All right, ladies and gentlemen, welcome back to section 4.6. We are starting our last topic of the year, related rates. Here we go. So, we're going to jump right into this. We're going to skip on down to example 2, okay? And what we're going to focus on in this chapter is the idea of looking at some sort of calculation over time. Okay, so for example 2 says air is being pumped into a balloon at a rate of 5 centimeters cubed per minute, right? So what does that mean for us? So let's take a look at a balloon that's being inflated over time. So I found a GIF here of a balloon that's getting bigger and bigger, right? And what we want to focus on here is that as the balloon gets bigger, right, what geometric properties are changing, right? As you're inflating more air into this balloon, what is changing? Well, its radius is changing as time progresses, right? As time progresses, I keep blowing air into the balloon, the radius gets bigger, its diameter gets bigger. But what else though? There are calculations for this balloon that would also change, right? Now, for the sake of making this a little bit easier on us, we're going to assume that our balloon in the example is going to be a perfect sphere. The balloon in this image is clearly not a perfect sphere, right? But this balloon still has a circumference that's changing, right? It's going to get bigger over time, right? The longer I let this GIF run, the bigger the circumference becomes, right? Same thing with its surface area, same thing with its volume, right? And so what we want to look at is what happens if I could pause this somehow. Can I pause this? No, I can't pause this. What would happen to this balloon if I were able to hit pause at some point while we were inflating it? Think of this like we're watching like a video, right? If I could hit pause, right, and measure how fast those measurements are changing, right? How quickly is the radius of the balloon changing? How quickly is the diameter of the balloon changing? Things like that, okay? And those are the rates that we are talking about. So let's go back and take a look at our example. Okay, air is being pumped into a balloon. Again, just to make our lives a little bit easier, we're going to say our balloon is a perfect sphere. Okay, air is being pumped into it at a rate of 5 centimeters cubed per minute. Now, units are really important in this section because not only do we need them in order to get full credit, but they actually tell us some really important things, right? And so if we focus on them separately, cm cubed, centimeters cubed, is usually a measure of volume, right? Minutes is usually a measure of time, okay? So V over T is 5, right? However, what we're saying though is if we are to follow this balloon's inflation over time, the rate of the volume increasing is actually going to be changing, right? It is changing. It is not the same increase when you first start blowing air into the balloon as it is when the balloon is almost completely filled, right? That makes sense, right? Once the balloon is almost at its maximum size, right, the rate at which the volume changes gets smaller, right? And so I'm not just going to call this V over T, this is dV over dt, okay, right? And this makes sense because think about what a derivative is. A derivative is measuring an instantaneous rate of change, right? And that's exactly what we're talking about here. There's some moment of time where the volume of this balloon is going to be changing at a rate of 5 centimeters cubed per minute, right? Later on, that rate of change is not going to be 5. It's going to be something else. But what we're talking about here is is at this moment, right, it is going to be 5, okay? And that's all we want to focus on for the rate of change of the volume. Now, the question says to determine the rate at which the radius of the balloon is increasing. So the rate at which the radius changes is going to be dr over dt. Every derivative and therefore rate we do in this section is going to be with respect to time, okay, right? Because the volume is changing as time changes, right? The radius changes as time changes, okay? And so dr dt, this is a rate of change I'm trying to solve for. So question marks, right? This is what I want, okay? Those are some bad question marks. Let's do that again. There we go. Those look a little better. Okay, that's what we want to solve for. Now, we want to know the rate of change of the radius of the balloon when the diameter of the balloon is 20 centimeters. So if we go back to our GIF here, right, if I were to pause this GIF at the moment the diameter was 20 centimeters, at that exact moment is when I want to figure out what is the rate of change of the radius, okay? So, diameter of the balloon is 20 centimeters. Now, this is actually a little bit tricky, right? Because ultimately, my goal is to relate the radius and the volume. So, diameter here is actually not necessary, right? This is not like what we did in the last section with differentials, right? This is a totally different topic, okay? So, I'm going to convert this into a R value of 10. Now, what's really important before we do anything else here is that you understand that the radius of the balloon is not always 10, right? Air is being pumped into this balloon, right? And so that R value, the moment we want to know what is the rate of change of the radius, right? At that moment, the radius is 10. This doesn't mean the radius is always 10, okay? And this is a key idea you have to think about when you look at these questions, okay? Okay. The topic is called related rates. In order to relate these rates, I first need to relate these variables, V and R. So what's the volume of a sphere in relation to its radius? Volume is going to be 4/3 pi r cubed. Okay, and now I'm going to take the derivative with respect to time. Okay, again, this is not differentials, right? I'm not taking the derivative with respect to the radius, right? This is a related rate question. All of my rates are going to be as time changes. So we're going to take the derivative with respect to time. Now, here's what that means. You'll notice in the volume of a sphere formula, there is no variable t, right? Because time doesn't affect how we calculate the volume of a sphere, right? And so that means what we're actually going to do here is implicit differentiation, right? We're taking derivatives of variables with respect to different variable, right? T. So let's follow implicit differentiation rules. So what's the derivative of v going to be, right? Well, it would be 1 dv dt. Okay, and on the right hand side, I would use the power rule. The 3 would come down, and so I would get 4 pi r squared. R is not t, so therefore chain rule, I have to multiply by my rate of change term, dr dt, right? So what I just did here was like those questions back when we were doing implicit differentiation in section 3.7, right? Taking the derivative of a y term with respect to x, I would have to multiply by dy dx. I'm doing the same concept here. I'm taking the derivative of an r term with respect to t, right? Therefore, I need this rate of change term, dr dt. Okay? But now, at this point, right, I have my related rate equation. I have an equation that relates all of the rates that I want to be related. And so now let's plug in my values. The volume is changing by 5 centimeters cubed per minute, so I can plug 5 in there. And on the other side, I have 4 pi. The radius at this moment is 10, and dr dt, that rate of change of the radius is what I am solving for. Okay, And so let's simplify. I still have 5 on the other side. 4 pi times 100 will give me 400 pi dr dt. Let's get dr dt, that rate of change term, by itself. So if I divide by 400 pi, I can simplify, right? 5 divided by 400, and I will get 1 over 80 pi in the denominator. Now, technically, that's my exact answer, right? And so we can stop right there, right? That is my exact answer. But I want to show you one other thing here that has nothing to do with related rates. I just think is a good calculator lesson. If you have a calculator with you, and honestly, you could even do this on your phone calculator, do 1 divided by 80 pi. Just type that in, 1 divide 80 times pi, right? And if you're thinking this is a really weird thing for me to ask you do, that's probably because you know that would get you the wrong answer, because that's not following order of operations, right? And so that would get you on the calculator 0.039, which is not correct, okay? And what you need to remember to do is, if you're typing this in on a calculator, make sure you're putting 80 pi in parentheses, so it's 1 divided by that quantity, and you get your actual answer, and your actual rate of change for the radius here, which is going to be 0.004, and now we solved for dr dt, right, which is the rate of change of radius over time. Now, dr dt, r and t, each of those has a unit of measure. R is going to be measured in centimeters because the volume was measured in centimeters cubed, and time is going to be in minutes. So the rate of change of the radius at the moment the radius was 10 is approximately 0.004 centimeters per minute. Okay, now honestly, exact answer is probably better, right? But I just wanted to talk about the calculator thing here real quick. Okay, don't forget units. Every answer we look at today and tomorrow is going to have units in it. Okay, let's take a look at another one. Example 3, which is really example 2 if you have your textbook. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment the rangefinder's elevation angle, so see if you can think, what's angle of elevation again? At the moment the rangefinder's elevation angle is pi over 4, the angle is increasing at the rate of 0.14 radians per minute. How fast is the balloon rising at that moment? This is a great example for all of you to pause this video, to be honest, and try to draw this scenario out yourself and see if you can come up with the equation that will relate the rates that are mentioned in this question. Okay, so if you want to do that, this is a really good example for you to kind of hit pause, analyze the scenario, right, and see what's going on. Okay, so if you want to hit pause right now, that would be great. Okay, I'm going to keep going here with this one. All right, so we have a couple of things going on here. Hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. Okay, so this is going to end up being a right triangle question. Spoiler alert. Okay, I'm going to label some things in this picture. So I'm going to have a liftoff point to start with. So I will call this LO for liftoff. And then I will put the rangefinder over here, RF. And then what's happening is that the hot air balloon is going to be up from the liftoff point. Okay? And now this is another good question for you to pause and practice even at this point, because if you're looking at a right triangle here, right, there are 5 different measurements besides the right angle. There's this side, which I will call X, that side, which I will call Y, and the hypotenuse, which I will call Z, right? And then there are a couple of angles here as well. I'm going to call this one theta, in the bottom left, and near the hot air balloon, I will label that as beta. Okay, so here's the thing I want you to think about. Okay, and you kind of have to visualize the motion in your mind, right? Because all you're going to be working with is a static image, right? But here's what you know: the hot air balloon is going to move vertically, right? So it's going to go up. So look at the 5 variables I have labeled in this picture: x, y, z, theta, beta. Which of those are going to change? Which of those are going to be constant, right? Now, I'll give you a second to think about this, right? But really, the answer should come pretty quickly because only one of these variables is constant throughout the motion of this hot air balloon, right? And that is going to be that the rangefinder is 500 feet from the liftoff point, and that would be our x. So I'm going to get rid of that variable and just put in a 500. Okay, that's going to always be 500. No matter what the hot air balloon does, the rangefinder is not moving. The liftoff point for the balloon did not change, right? No matter where the hot air balloon goes, this was always its liftoff point, which was always 500 feet away from the rangefinder. Okay, so that's the only thing here that's constant. Okay, now the other thing I want you to focus on is, okay, let's look back at the question now. Which of these variables matters? Because not all 4 of these variables is going to be important in this question, okay? So let's take a look at this. At the moment, the rangefinder's elevation angle is pi over 4. Now, this to me does not look like a fixed angle because it says at the moment, right? So this is going to mean, like we were looking at that GIF, if we could pause the movement, if we could pause the action, at one particular moment, the rangefinder's elevation angle is pi over 4. Now, which of these is going to be an elevation angle, theta or beta, right? And so hopefully you remember that it is theta, right? It is from the horizon going up. That's an angle of elevation. So that is the angle we are talking about here. Now, don't get crazy here and write pi over 4, right? Again, think about the motion of this hot air balloon, right? And I'll kind of draw this real quick and then I'll erase it, right? If the hot air balloon goes up even more, right, then the elevation angle from the rangefinder is going to be bigger than pi over 4, right? That's going to get bigger. So it's not going to always be pi over 4. This is a really important concept for you to understand. What is going to change as a result of the motion we're talking about, right? So I'm going to leave that as marked theta, but at this moment that we care about, theta is going to be pi over 4, okay? The angle is increasing at a rate of 0.14 radians per minute. Now, this is also important, right? Because we're talking about this angle theta, so this is now the rate of change of theta, d theta dt, radians per minute. Remember, all calculus is done in radians, right? Radians per minute is 0.14. Okay, so there is a rate, right? That is one rate given, and now this question is asking us, how fast is the balloon rising at that moment? And now let's take a look at my variables y and z. Which of those would represent the balloon rising? Would that be z, the hypotenuse, or y, the vertical? Well, that should be y, the vertical. So yes, the hypotenuse will change. I just don't care about it in this question, right? I care about the rate of change of y because that represents how fast the balloon will rise at that moment. So I'm looking for dy dt. So I have 2 rates here, right? dy dt I do not know. D theta dt I do know. I want to relate the variables y and theta in this scenario. Okay, and so how can I do that, right? How can I connect these two? And now this is where it's helpful to remember that we drew a right triangle, and what are some things we do with right triangles? So a lot of people will default to Pythagorean theorem. That is not correct, right? And what we should try to remember is what we did all of first semester, which is Trig, right? Let's set up a trig equation because I have an opposite and an adjacent for my angle theta. And so that means I can set up a tangent of theta equation as y over 500. And I will take the derivative of this equation with respect to time t. Again, there is no variable t in my tangent equation, right? So I'm doing implicit differentiation. Whenever I take the derivative of theta and y, I will have to multiply by the rate of change terms, dy dt, d theta dt, right, because of the chain rule. So take your derivatives like normal. What's the derivative of tangent, right? Hopefully we remember that that is secant of theta squared. And we will multiply this by dy dt. Oh, excuse me, wrong variable, d theta dt. And on the other side, y over 500. Now, if you want to do the quotient rule for this, you're going to waste a lot of time, right? You can think of y over 500 as 1 over 500 times y. Think of it as linear. And so the slope is 1 over 500. And now my rate of change term is dy dt. And now here is my related rate equation. And so now let's go ahead and plug everything in, okay? So let's plug everything in, right? Secant of theta squared, theta at this moment is pi over 4, so secant of pi over 4 squared. Now I'm going to do myself a little favor here. This 1 over 500 on the other side, I'm going to multiply over, so I get just 500, right? And then d theta dt is going to be 0.14. And that will leave me on the other side with just dy dt. Okay, and so dy dt is already isolated, which is good. That's the rate I want to solve for. And now let's think back to trig here. Secant of pi over 4 is the reciprocal of cosine of pi over 4. So cosine of pi over 4 is root 2 over 2. Take the reciprocal, we get just root 2. Square it, and we get 2, right? And so 2 times 0.14 times 500. 2 times 500 is 1,000. 0.14 of 1,000 is 140. And that's a nice exact value for dy dt. And so the last thing I need for this is units, right? And so let's look back at the question, right? We had 500 feet for the distance between the rangefinder and the liftoff point, so we can use feet for distance, and time is again in minutes. And so I can say my final answer is 140 feet per minute. Okay. So that is a really good question to take a look at, right? Because we're going to be doing these examples with right triangles, right? This is not a Pythagorean theorem question, right? You typically, whenever you have a rate that involves an angle changing, it's going to not be Pythagorean theorem. You're going to want to think about a trig equation for that. Okay, that's a little hint there for the future. All right. Okay, let's look at example 4. This is a fun one. Water runs into a conical tank at a rate of 9 feet cubed per minute. Okay, so a couple of things. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. Okay, before we take a look at this scenario, I want to show you guys another GIF. So I'm going to go back to Chrome here, and I have this GIF that I like. Okay, filling up a cup of water. So you may have a glass at home, a simple glass, right? Put it under the faucet, under the Brita, right? Whatever you use, and let the water fill up, right? And what I want you to notice is, what shape does the water take when you're filling up a glass of water, right? And if you have a basic glass, kind of like the one this GIF is showing, then the water should take the shape of the glass, right? That's an important idea here, okay? That's a very important idea. Whenever you see this sort of question, and this is a very common question in calculus, of some sort of object being filled up, with a liquid, or like sand is pouring into this tank or something like that, right? But if you look at the water inside the cup, right, inside the glass, it's taking the shape of the glass, right? That's an important idea. Now, this particular glass, you may remember from geometry, is a frustum, right? Which is a cone that's had like the point cut off, okay? And so what you're seeing then when you fill it up with water is that the water is also in the shape of a frustum, okay? This is a really important idea here, okay? Now we're going to deal with a cone that's standing upside down and has a height of 10 feet and a base radius of 5 feet. Now, what's really important here is that you don't confuse what the 10 and the 5 represent. These are dimensions of the tank, my conical tank. Does the tank change? Is the tank's height and radius changing? No. Those are constant, right? Those are constant. And so I already have my cone drawn here, right? And so this cone, right, and we're going to assume it's a right cone just to make things easier. And you can do this with all shapes unless it says specifically like this is a slant cone or something. Spoiler alert, that won't happen in this class. But what we can do here is we can label now that the height of the cone is 10 feet and the base radius of the cone is 5 feet, right? And now what's going to happen is that as water gets poured into this tank, right, the cone of water is the cone that is changing, right? And so I'm going to label the cone of water to have an H and an R, right? Because those two are not constant, right? As more water comes into this, right? As more water comes in, right? Oh, I picked the wrong color, dang it. But you get the idea, right? The height would get greater, the radius would get greater, right? That is the cone whose dimensions are changing, okay? So that's the cone we want to focus on, all right? So what does it say to look for? Okay, well, let's come back in here. Water runs into a conical tank at a rate of 9 feet cubed per minute. So again, feet cubed, that's a rate of change of volume per minute. So that's over time, and that's going to be 9, right? And that's going to change the volume of the cone of water, right? The tank, that cone, its volume is fixed, right? Height of 10 feet, base radius of 5 feet. You could calculate the volume of the tank. That's not what we're trying to do, okay? Right? The cone of water, its volume is increasing 9 feet cubed per minute. I want to know how fast is the water level rising. So again, I'm looking for some rate. So now you have to think about this. Water level rising, would that be the rate of change of the radius of the cone of water? That doesn't make sense. Let's go with the height. So dh dt is what I'm solving for, right? And that I do not know. So I'm trying to relate rate of change of the volume to the rate of change of the height, okay? When the water is 6 feet deep, so when h is 6, at the moment that h is 6, that doesn't mean I'm going to cross off h here and put 6, right? Because the height is going to change, right? You're going to pour more water into this tank, right? And I know that because it has a positive rate of change for its volume, right? By the way, quick fun fact, if the rate of change of this volume was negative, that would mean that water was like leaking out of this cone, right? That would be a negative rate, but we're not going to worry about that right now. Okay, so I will give you volume of a cone formula, so you don't have to go Google this or Wikipedia this. Volume equals 1/3 pi r squared times h. Okay? Now, this brings up a really, really huge problem for us, right? And that is, this class is typically considered to be single variable calculus. And what by that we mean single input variable, right? Volume, in this case, is a function of both R and H. That's a huge problem for us, right? Because if I were to go right ahead and take the derivative with respect to time, on the right-hand side, r squared h, I would have to do the product rule, right? And if I did the product rule and I were to take the derivative of this r squared term, that would leave me with a dr dt term. Now, some of you might go, okay, that's just another rate, right? And we know the radius is also changing, so why is that a problem? Well, the reason it's a problem is because I have no information on the rate of change of the radius, right? I don't have it as a given, right? And I'm not trying to solve for it, right? What the heck is dr dt going to be? Okay? And this is where this particular type of question leads us to doing something a little bit fancy. So I'm not going to take the derivative of this volume equation right away. Instead, what I'm going to do is I'm going to compare my two cones here. Okay, my cone for the tank and my cone of water inside that cone. Okay, and what you should notice is that both of these cones are similar. Okay, right? In terms of the geometry word, similar, right? These are similar shapes, right? And more importantly, what I'm going to focus on here are the similar triangles inside of my similar cones, right? And so I'm just going to focus, for example, like on this big triangle for the cone, the tank cone, and then for the water cone, right? These are similar triangles. They're similar by angle-angle similarity. You do not need to remember that for this, but you should, right? If two triangles have two pairs of angles that are congruent, well then by AA, right? Or it's the no choice theorem from geometry that says the third angles would have to be congruent, right? So ultimately, that's why they're similar. You don't really need to prove any of that. You just have to recognize it, right? And that's exactly what I'm going to focus on here. So the tank is a height of 10, a radius of 5. The cone of water has a height and a radius. And something you may remember from geometry class is when we have similar shapes, right, their sides have to be proportional. So we can make a proportion. So I'm going to go R over H, right, for my cone of water is to the cone of the tank 5 to 10, R to H, right, radius to height. And now what I can do is I can cross multiply and I can get 10R equals 5H. Okay. So 10R equals 5H, and now I have an equation that relates R and H, right? And so I'm going to divide by 10, and I'm going to say that the radius, again, what does R refer to? R refers to the radius of the cone of water, right? R has to equal always half of H because it is similar to the conical tank, right? And that's the ratio of that tank, right? 5 to 10 is 1 to 2. The radius always has to be half the height. Now, why did we take this little detour? Well, that's because now that I know what R equals, I can plug it in, right? Before I take a derivative. I can plug in this value for R, and that will leave me with volume just in terms of H. So I can get that the volume is going to be 1/3 pi, and now I can replace R with 1/2 H. Remember, it's R squared, so 1/2 H is now getting squared times another H. Okay? And now a lot of people will look at this and go, oh, great, now I can take the derivative, right? No, do not take the derivative of this yet, please, okay? Instead, what you can do is simplify, because if you don't simplify, you're doing chain rule and product rule, and you're making your life harder, okay? And I don't want you to do that. So let's simplify this. What does volume equal? A half squared is a fourth times a third gives me a 12th pi, and I had h squared and another h outside, so that leaves me with h cubed. Please, please, please simplify before you take a derivative, okay? And now I can take a derivative with respect to time, right? And so on the left-hand side, I will get dv over dt equals 1/12 pi times h squared times dh dt. And here is my related rate equation. And now I can go ahead and plug everything in. And so dv dt, oops, I'm sorry, I know dv dt, it's 9, right? And so I'm going to get, let's see. Oh, whoops, I did this wrong. Sorry, let's go back up here. I made a boo-boo. The 3 comes down. This isn't 1/12. That's supposed to be 1/4. Whew, good thing I caught that. Okay, here we go. So this is going to be 1/4 pi times the height at the moment we're trying to solve for dh dt. The height at that moment is 6, so I can plug that in. And then I have dh dt. And now 6 squared is 36, divided by 4 is 9. 9's on each side cancel, so I can move the pi over, and so I get that dh dt is 1/pi, and now everything was measured in feet, and time was in minutes. Okay, so this is a little bit of a tricky question, okay, right? You have to look at that volume formula and notice there are two kind of like input variables, right? And now in this case, both R and H were not constant, right? And so we got to figure out a way we can get rid of one of those, okay? Now, I'm going to show you one more way of doing this question that's a little bit harder, okay? Now, you might look at this and go, boy, there's a harder way of doing this. Yes, there is, okay? Now, I've copied most of the work over, okay? And basically what we're going to do is, well, what if we had done our very bad idea of taking the derivative of the volume formula right away? Well, it's a bad idea, but it's not impossible, okay? So I just want to show you what that would look like, right? So on the left-hand side, you would get dv dt, right? I'm going to leave the 1/3 pi outside of my product rule, and then I can distribute it in at the end, right? But r squared times h, you have to use product rule for that, okay? So I'm going to take the derivative of the r squared term first, so that would be 2r. The h is going to stay, right? But since I took the derivative of r, I need to multiply by dr dt. Now, this is the problem I was describing in the previous example, right? I don't know dr dt, right? We still have that same problem, right? I don't know what dr dt is, and the question is not asking me to solve for it. So we do have a workaround, though, which is what I'm going to show you in a moment. Let me finish doing my product rule here, right? So the r squared will stay, and then the derivative of h, that's just 1h, right? So the derivative will be dh dt, okay? So here is a related rate equation, right? I'm relating the rates of dv dt to dr dt and dh dt. But again, that's a problem because I don't know what dr dt is. So here's what we can do. Basically, once you recognize the similar shapes and get r equals 1/2 h, once you get that, you can actually take the derivative of that equation as well with respect to time. And you can get that dr dt is 1/2 dh dt. So we can actually come up with a value for dr dt and plug it in. So that's exactly what we're going to do. Now, again, I'm going to go through all of this. I think this is more complicated. So I would not encourage it, but I just want to show you that it is possible. Okay, so let's go through this, right? So I'm going to get dv dt. I'm going to leave the 1/3 pi again out. Okay, and so I'm going to get 2rh, and then I'm going to replace the dr dt with my 1/2 dh dt. And then I had r squared dh dt. Okay, now another problem with doing it this way is that the question originally told us when the height was 6. It didn't tell us what the radius was at that moment. Well, I mean, we can solve it pretty quickly, right? R is half of h, so if the height is 6, radius has to be 3, right? Okay, so let's calculate dv dt. Oh, I'm sorry, we know dv dt. That's not what I want to calculate. dv dt is still 9, equals 1/3 pi, right? And then I get 2. R at this moment is 3. Height was given is 6. And then I'm going to get times 1/2, and dh dt is what I'm solving for. And r, again, at this moment, we have to solve for this, right? We know the height is 6, but r is, again, half of h, so we know r is 3. 3 squared times dh dt. And now it's just a matter of getting my dh dt's combined. One thing I'm going to do real quick, I'm going to multiply a 3 over to the other side to get rid of that fraction, so I get 27 equals pi. And now 2 times 3 is 6, times 6 is 36, half of which is 18 dh dt. 3 squared is 9 dh dt. And so I'm going to get 27 equals 18 plus 9, 27. I have a pi out front. I get 27 pi dh dt. The 27s cancel. Divide the pi over to the other side. I get 1 over pi dh dt, which is ultimately the same thing I got doing it the other way, which I think involved a lot less work and an easier derivative. So if you're a glutton for pain, this is definitely the way to go. I do not recommend this, okay? But again, I just want to show you it is possible, but if you're ending up doing a product rule or something like this, you're doing too much work, okay? If indeed both of these are variables, r and h, right, and they are going to change, there's probably a way you can substitute one of them out, or maybe one of them is a constant. That would be nice, right? But not the case in this question. So again, moral of the story is do it this way. It's a lot quicker. Okay, that's it. I will see you next time.